Hi, my name is Wang, and I'm excited to present our work on emergent prosociality in multi-agent games through gifting, which has been an awesome collaboration with great people from Stanford and UC Santa Barbara. Coordination is often critical to forming prosocial behaviors, or behaviors that increase the overall sum of rewards received by all agents in a multi-agent game. For example, we can take the age-old question, how many minions does it take to screw in a light bulb? And here, some of the minions call for help to try to reach this light bulb, and it appears that they're about to succeed. But this minion on the left selfishly finds joy in watching this unstable minion pyramid begin to wobble. Even a single defector can make an entire equilibrium unstable. So the answer seems to be that all the minions are necessary to screw in the light bulb, as cooperation is key. And the key problem is that even one selfish agent can lead to coordination failure. And however, this problem is not unique just to minions. In the real world, coordination is often coupled with risk. There are many applications where there's a safe equilibrium that leads to guaranteed but low rewards, and a risky equilibrium that leads to higher rewards only if the agents cooperate. When multiple equilibria exist, uncertainty in the opponent's actions can cause single-agent reinforcement learning algorithms to converge to socially less desirable equilibria. For example, there may exist a selfish equilibrium that provides a decent reward regardless of opponent behavior, and there could be a prosocial equilibrium that would only be reached if agents are confident that the other will coordinate. So when uncertain about the other agent's actions, the agents, depending on their initializations, will more often choose to go to the selfish equilibrium. And similarly, here the green agent's uncertain about the red agent's actions, so they converge to the socially less desirable equilibrium. And it turns out that prior works have shown that when confronted with this coordination problem, not just state-of-the-art reinforcement learning algorithms, but humans alike often choose the greedier, socially less desirable equilibrium. Instead, we should hope that we can train our AI agents to be prosocial and find the more socially desirable equilibrium that maximizes the benefit for all entities in the environment. Previous works address this problem of reaching the prosocial equilibrium by focusing on using explicit reward shaping to force agents to be prosocial, such as forcing each agent to maximize the reward of all agents in the environment. And although successful, these approaches require the strong assumption that an agent's reward function can be externally modified and that an agent can be forced to be prosocial and care about maximizing the total utility of all agents. Instead of explicitly redefining their reward functions, Lupo et al. Recently proposed a peer rewarding mechanism to allow agents to optionally share their rewards. And we investigate gifting's potential to encourage prosocial behavior. And our key insight is that gifting, a decentralized peer rewarding mechanism, can mitigate risk and encourage prosocial behavior without explicit reward shaping. And critically, unlike explicit reward shaping, gifting is decentralized and allows agents to retain their self-interest and only imbues agents the ability to gift each other rewards if they so choose. In our work, we're primarily focused on normal form coordination games, where the rewards can be represented by a payoff matrix, and we're most interested in the stag hunt game because of the difficulty associated with reaching the prosocial equilibrium, as I'll now explain. So the first agent shown in red is represented by the rows, and the second agent shown in green is represented by the columns. Both agents choose between two actions, hunting the stag and foraging for mushrooms. If both agents choose to hunt the stag, they succeed and are rewarded greatly, while if only one of them goes hunting, they return empty-handed and injured. On the other hand, foraging mushrooms guarantees a meal for the night, although not quite as satisfying. The agents choose their actions simultaneously, so as an example of payoffs, they can choose hunt to receive the highest reward of 2, they can choose hunt forage, or they can choose forage hunt, and in either of these cases, the agent who hunted alone got the lowest reward possible of -2, as the other agent did not cooperate. And finally, they can choose forage to receive a guaranteed reward of 1. So which of these are considered pure strategy Nash equilibrium? Or more precisely, in which outcomes would neither player benefit by individually changing their choice of action? So let's look at hunt. We can see that if either of them deviates, it will hurt their reward. And now we can look at the other equilibrium, forage. And again, any single agent deviating would reduce their individual reward. So the hunt equilibrium is better for all agents, but there's a risk of hunting the stag alone. So selfish agents tend to choose this less prosocial forage equilibrium because of the risk, despite hunt being universally better. So this is a classic game theoretic example where multiple equilibria exist with a prosocial and a risk-dominant equilibrium that would be preferred if agents are uncertain about the other agent's actions. So we propose using zero-sum gifting, where each agent has an extended action space with extra actions to send rewards to each other as gifts in a zero-sum manner, following the principle of what I give is what I lose. In these one-shot coordination games, we prove that zero-sum gifting does not introduce new equilibria. So here's the general matrix for stag hunt. H refers to the reward for hunting together, F is the reward for foraging together, C is the reward for foraging alone, and R is the reward for hunting alone, which characterizes the risk in the game of stag hunt. As R decreases, the risk in stag hunt increases monotonically. So what happens to this payoff matrix when we introduce gifting? So we're allowing agents to give away a constant part of their reward by subtracting from theirs. So each agent's action space is doubled, since they can now simultaneously gift while choosing between hunt and forage. So let's see how gifting impacts the payoffs. Take, for example, the scenario where the red agent hunts and the green agent forages. We know the outcome of this from the original table, but what happens when the green agent decides to help out the red agent by giving them a gift? So we can see that the red agent's reward increases by the gift amount gamma, while the green agent reward decreases. Now, what happens if both agents simultaneously gift? Well, these agent actions cancel out and they receive the same reward. And following this fashion, we can fill in the remainder of the table. And what's important to note here is that the pure Nash equilibria have remained the same, although new actions have been introduced, which we prove in our paper. This can be explained intuitively since any action that contains gifting cannot be a part of the pure Nash equilibrium, since that agent can receive a strictly higher reward if they choose just not to gift. And while at first glance, one might expect the other diagonal entries to be equilibria as well, you can see that in either of these cases, a single agent can just choose not to gift and receive a larger reward. And so we can think about this intuitively. Why do we expect gifting to help our agents reach this prosocial equilibrium? So we know that stag hunt's risky due to the penalty caused by hunting alone. And the agent who chooses to hunt alone will be disincentivized from ever hunting again due to the poor reward that they received that turn. And by default, without gifting, we expect the inherent risk to ground the players to choosing this safer, risk-dominant pure Nash equilibrium where they both choose to forage. And so why do we expect gifting to help mitigate this effect? We can see that with gifting, even if a player decides to hunt alone, there's a chance they will receive a good reward because the other player may give a gift to our hunter. And although this action doesn't bring the player directly to the pure Nash equilibrium, the prosocial equilibrium, it mitigates the risk of hunting and hence increases the probability that agents converge to the prosocial equilibrium. And in our work, we show that gifting encourages prosocial behavior while allowing agents to remain selfish and decentralized, both through analysis of the learning behavior as a dynamical system, as well as through model-free reinforcement learning experiments. So to carefully inspect the effects of gifting on stag hunt, we formulate the learning process of the agents as a dynamical system and show that gifting increases the basin of attraction of the prosocial equilibrium. So first, we define the policies of the two agents as pi x and pi y. X parameterizes agent 1 and y parameterizes agent 2. Sj represents the actions hunt, forage, hunt plus gift, and forage plus gift, respectively. We can then write the expected rewards as follows, where mu is the payoff for taking actions S1 and S2. And while RL methods employ various methods to estimate value functions or policy gradients, the true gradients can be closely estimated here by collecting large batches of data, since this is a one-shot game. And so we have the true gradients here as follows. Since both agents are self-interested, we then assume that they want to maximize their reward, so they update their policies based on these gradients. This formulation leads to an 8-dimensional autonomous dynamical system as follows, where Z is X and Y concatenated together. This formulation is general to any two-player, 4-action, normal form game, but we focus on stag hunt to see the effects of gifting on this dynamical system. Specifically, we can analyze the dynamical system's equilibrium behavior in the form of basins of attraction. So we can compute the basins of attraction of the equilibria, which are the initial states of the system that lead to the specific equilibrium. And this is possible because we know the stable equilibria a priori. So the axes of these plots correspond to the parameter spaces of the agents, and we color them based on the likelihood of reaching the prosocial equilibrium. So as you move to the top right of the plot, the agents are initialized with a higher likelihood of taking the hunt action relative to the forage action, which is closer to the prosocial equilibrium. So the left heat map shows the basins of attraction without gifting. And the white region shows the area of the parameter space that converges to the prosocial equilibrium. And you can see the basin of attraction of the less socially desirable equilibrium is much larger in black. The right heat map corresponds to the extended game with zero-sum gifting actions, where you can see now that more initializations converge to the prosocial equilibrium. And this blue line shows the boundary for the game without gifting, for comparison. And overall, this shows gifting is indeed beneficial for getting prosocial behavior in the equilibrium, as the prosocial equilibrium's basin of attraction has now increased. And in the dynamical system, we assumed access to the true gradients and rewards. But we further validate our results in more realistic learning settings, where the payoffs of the agents are unknown a priori. And for all these experiments, we train a deep Q network for each agent, and we show that zero-sum gifting increases the probability of converging to the most prosocial equilibrium in a variety of coordination games. So in Bach or Stravinsky and pure coordination, all equilibria are equally prosocial. So we converge to one of these equilibria 100% of the time with and without gifting. In assurance, there's no risk, making the prosocial equilibrium a favorable outcome even without gifting. But we still see an improvement when adding these gifting actions to the agents. And for stag hunt, we examine 3 variants of stag hunt with varying risk. We see that gifting has a greater benefit when the risk is higher, but performance does diminish slightly in the low risk setting. Overall, in the experiments, we see that gifting is more useful in riskier scenarios. And in the FC3 and FC4 stag hunts, we go beyond dyads and look at n-player games where each pair of agents plays a stag hunt against each other simultaneously. In these n-player games, we can see that gifting does help increase the probability of convergence to the prosocial equilibrium, but as the number of agents increases, it becomes more difficult to coordinate all agents and encourage risky prosocial behavior over those safer actions. More agents creates more uncertainty about the other agent's actions, which encourages risk-averse actions as opposed to coordinating actions. And finally, we have repeated stag hunt, where we go beyond one-shot games and examine stag hunt repeated over a finite horizon. Gifting significantly increases the probability of convergence to the prosocial equilibrium. And when comparing the repeated stag hunt results to the corresponding one-shot medium-risk stag hunt, we can see the likelihood of agents coordinating decreases both with and without gifting, implying that coordination over repeated instances of stag hunt is a more difficult, risky setting. And we further examine the relation between gift value and risk value in stag hunt to better understand how risk impacts gifting. The results show here that in order for gifting to help in coordination games with higher risk, the gift value needs to increase to compensate for the added risk. Notice that as the risk increases, or as we go to the left of this x-axis, the necessary gift values to be beneficial increases along the y-axis as well. This should make sense, as the gift value must scale relatively to the risk in order to be risk mitigating. So to recap, our key contributions are as follows. First, we proposed using a zero-sum gifting mechanism to encourage prosocial behavior in coordination games, while allowing agents to remain decentralized and self-interested. Second, we provide insights on the effects of zero-sum gifting for n-player one-shot normal form games by formally showing that they do not introduce new equilibria. And finally, we experimentally show that gifting increases the probability of convergence to the prosocial equilibrium in general sum coordination games when agents are trained with deep Q networks. So I hope you found this interesting, and I hope you check out our paper for more details. Thanks.